Today, I'll be presenting to you some of my master's research, evaluating Energiesprong retrofits for solid masonry townhomes in Toronto. Just before I start off, I'd like to thank the Passive Buildings Canada team for giving me this chance to share with you a bit of my passion about retrofits. I volunteered at this event while I was a student for the last 2 or 3 years, and I've been doing things like giving out name tags to serving you drinks because Greg didn't know where to put me. And it's nice that's kind of like a full circle that I get to now present for you all. So thank you very much. All right, so through this presentation summarized here, the reasons for why this research is needed, the questions driving the work, the analyses completed, and the results obtained will be shared. The City of Toronto has set itself a goal of achieving net zero emissions performance in the next 16 years. That includes a 100% reduction in greenhouse gas emissions by 2040 relative to 1990 level of GHGs. While the transportation and waste sectors account for 35% and 9% respectively of Toronto's overall emissions, the building sector alone accounts for 56%. In terms of building types, residential buildings are responsible for 60% of the building sector's GHG emissions. Now this includes multi-unit residential buildings whose share of 29% represents one of the most important contributions to GHG emissions by building type. Now, from the building sector's consumption, primary energy consumed stems from necessities such as space heating, cooling, and ventilation. The energy sources for these uses are generally either electricity or natural gas. In 2019, 92% of the province's electricity was produced by non-fossil fuel sources, primarily by nuclear generation, which accounted for 59%. However, nuclear-generated electricity production will slow significantly in the coming years, as many of the province's nuclear generating stations require refurbishment or are at the end of their service life. The Pickering nuclear generating station shown here is a prime example, as refurbishment will stop its energy generation, thus negating the 14% of Ontario's energy it would normally supply. Putting this all together, what could this mean for the City of Toronto? Well, the building sector is responsible for such a significant portion of the city's GHG emissions, it's evident that one target area to focus in on is the building sector's energy consumption. Unless this is done, there is a risk of the Greater Toronto Area's emissions increasing by 2.25 megatons of CO2 equivalents per year. This will undoubtedly represent a step backwards in Toronto's path to net zero. So, what's one possible solution to consider? You all know it, it's deep retrofits. Now I know I'm preaching to the choir, but let's talk about deep retrofits for a second. To reduce the amount of energy consumed from the built environment, deep energy retrofits are often implemented to improve a building's performance. Typically, deep energy retrofits target energy consumption reductions of at least 50% or more. However, the widespread adoption of deep retrofits has been limited because of factors such as extensive disruptions or high costs. On the other hand, conventional retrofits often include partial renovations or isolated upgrades to the building. These achieve up to 25% energy consumption reductions. These smaller scale retrofits are usually prioritized by the general population due to shorter payback periods and limited disruptions to the occupants. In the end though, significant and extensive improvements to our existing building stock must be completed to reduce our greenhouse gas emissions. The question then is, how can we prioritize a bit of both of these strategies, maximizing energy reductions while limiting occupant disruptions and creating economies of scale over time? Enter the Energiesprong retrofit strategy. Energiesprong was started in the Netherlands with the overarching goal of industrializing the deep energy retrofit process at low financial cost while providing a high quality product. This accelerated retrofit strategy utilizes prefabricated panels to enclose buildings in a super insulated envelope to reach net zero energy levels of performance with renewable energy systems. Given its prefabricated nature, on-site labor for an Energiesprong retrofit can generally be completed in 1 week of work, all the while remaining primarily to the exterior of the building, thus minimizing occupant disruption. The Energiesprong methodology, which has become popular in Europe, could serve as a basis for an existing building retrofit framework in Toronto that is both scalable and repeatable, crucial characteristics of the needed retrofit strategy for the city to reach its net zero goals. The Dutch Energiesprong model initially used social housing as its target market, the success of which could potentially be carried forth in Toronto. Toronto Community Housing, the largest social housing provider in Canada, has a portfolio that is well suited for the large-scale implementation of an innovative deep retrofit strategy. More specifically, TCH's low-rise solid masonry archetype lends itself towards panelized retrofits, as its few geometrical variations must be accounted for, meaning they're simple box buildings. Furthermore, their existing low-rise MERB stock already requires significant repair and maintenance. The TCH portfolio could therefore serve as an ideal candidate for the beginning of mass Energiesprong retrofits in Toronto. However, the overclad of solid masonry buildings would require proper study, as the masonry properties could significantly alter the wall's hygrothermal performance post-retrofit. This would not only impact the structure's durability over time, but poor hygrothermal performance of the envelope could result in loss of energy saving potential, as well as affect occupant health. There are many factors at play in this kind of retrofit, some of which are listed in this right here. Given the significant stock of this building archetype, it's important to know what kind of overclads are feasible and which ones are not. With all of this in mind, the following question guided a portion of my research. How do masonry moisture storage, initial moisture conditions, and panel type affect the performance of panelized retrofitted wall assemblies for low-rise solid masonry residential buildings? The objective of this research was to help inform both Toronto Community Housing as well as the industry of the potential consequences of retrofitting solid masonry buildings using panelized approaches if various conditions are not accounted for adequately. This would be demonstrated through the creation of a testing of a hygrothermal performance sensitivity analysis methodology on a pilot building, namely a TCH low-rise solid masonry townhome. All right, I know I spewed a lot of information, so let's do a quick recap. Toronto wishes to hit net zero by 2040. We therefore need to reduce our greenhouse gas emissions from the building sector, namely in MERBs. TCH has a large stock of buildings that could be targeted, many of which are low-rise solid masonry ones. To both reduce costs of retrofits while limiting occupant disruption, the panelized Energiesprong approach should be considered. However, as with any retrofit, hygrothermal performance is of crucial importance for masonry retrofits. This is where the significance lies for the hygrothermal performance sensitivity analysis methodology that we created here. So let's talk about the pilot building a bit. The building used as a test subject for this research is a 6-unit, 2-story townhome located west of Toronto. The pilot building, Building C, shown on the right, is a very similar design to that of a community surrounding it that belongs to Toronto Community Housing. The overall geometry of the building is quite simple, box-shaped with flat exterior walls. The wall buildup is shown here and includes a 1/2 inch of interior plaster finish, 1.5 inches of rigid insulation, a 1/4 inch of cement mortar adhesive, 4 inches of concrete block, and a 4-inch brick finish. To better understand the effects of panelized retrofits on solid masonry buildings, a methodology was created for modeling various overclad wall assemblies to analyze hygrothermal performance post-retrofit. The first step of the methodology is to define and understand the existing assembly being studied. In our case, the existing assembly is a solid masonry wall with a face brick and block backup. Brick type serves as the second consideration in this methodology that we created. Solid masonry wall assemblies are known for their ability to store large quantities of water as the sole water-shedding surfaces for these structures. For this reason, it was especially important that the type of masonry in question be studied, as all bricks generally possess a different moisture storage function. This will greatly impact the ability of the wall assembly to dry out over time. In our case, the pilot building did not have any masonry testing conducted. For this reason, a high reservoir brick and a low reservoir brick are being compared in terms of their post-retrofit performance. By reservoir, we refer to the masonry's moisture storage abilities. As seen on the right, the two brick types modeled possess very different moisture storage abilities, about 28 times more in the high reservoir brick at 100% relative humidity. This is where EMC conditions come in. EMC refers to the equilibrium moisture content of a material at a specific relative humidity. For instance, EMC 80 would represent the moisture content in the masonry at equilibrium with 80% RH. It's important to vary this parameter. Industry often takes EMC 80 as its starting point for hygrothermal modeling, but industry experts have seen this number climb up to EMC 100 for masonry, which is an immense difference in terms of how much moisture is in the assembly. For this reason, the brick masonry was simulated at varying initial moisture content levels. EMC 80 was tested given its industry normal use, followed by increasing EMC conditions until EMC 100. EMC 60 and EMC 70 were also modeled to determine if drier systems could achieve more favorable results in terms of hygrothermal performance. Comparison of multiple panel types allows for contrasting between a desired panel and other industry standard panel types. Now, Natural Resources Canada recently put out a guide to panelized retrofits and considerations. As outlined in that retrofit guide, panel-related factors that should be considered include the panel's outward drying potential, thermal resistivity, and embodied carbon. Therefore, based on their differences in these three parameters, the use of a wood frame cellulose insulated panel was compared to the use of an EPS insulated SIP panel, or structural insulated panel. To account for errors in construction, unforeseen climate events, and more, stressors are often added to the models to analyze how the assemblies react. Rain leaks behind the water-resistant barrier were tested for this research. ASHRAE 160 indicates a 1% rain load can be placed on the outside of a WRB as an added stressor. However, other research has shown that something more impactful could be the introduction of 1% or even 10% of that rain load directly placed in the outer sheathing. These two stressors were chosen for this research. Finally, to quantify the assembly's hygrothermal performance, criteria must be defined. This will allow designers to decide whether there exists real risk of failure of the assemblies over time. These models were studied for three things. Number one, moisture accumulation, meaning checking if there's accumulation of moisture over the simulated periods throughout the wall assemblies. Number two, mold growth potential at key areas within the assembly's air barrier layer. And number three, decay, meaning checking if wood-based products experience higher than 20% water content over the simulated periods. The software that was chosen for our research was WFI from the Fraunhofer Institute in Germany. Shown here is the cellulose panel retrofit assembly as it is represented in WFI. Note that the yellow triangles indicate where mold growth within the post-retrofit assemblies was tested using WFI. These locations were chosen based on the material type, their position within the air barrier of the wall, and their proximity to the indoor space. The same is shown here for the post-retrofit SIP wall assembly. Now the following slides have color-coded results of the hygrothermal sensitivity analysis based on whether the three performance criteria were satisfied or not. A green box indicates that the performance criterion was satisfied. A yellow box, used only for the mold criterion, indicates that there may be potential mold issues. And the red box indicates that the performance criterion was not satisfied. So before I dive into the results, let me quickly point out a few things on this very large and unfortunately complicated graph. The top half is the cellulose insulated panels results, while the lower half is the EPS insulated SIP panels results. The left half is for the low reservoir brick. Right half, as shown, is the high reservoir brick, and then each of the columns represents the different performance criterion that were studied in this research. Starting with starting with moisture, the next three being the mold locations that were studied, and finally decay for each of the brick types. Here I'd like to draw your attention to the fact that at the industry recommended modeling level of EMC 80, the cellulose panel that was modeled has potential issues across the board already, with unacceptable performance in terms of mold in both brick types. This SIP panel, insulated with EPS, on the other hand, seems to perform quite well. However, at the EMC 95 condition, you can already see how things are getting even more worse in terms of performance, with the same failed criteria in the cellulose panel, but new issues in terms of mold with the high reservoir brick with the SIP overclad, and even potential issues in the low reservoir brick for the SIP overclad. At the EMC 100 level, the moisture contents are significantly larger than the other initial conditions studied. At this point, there are failed criteria across the board in both the cellulose and SIP overclads for both the low reservoir and high reservoir brick types. Further simulations were conducted to determine at which EMC level below EMC 80 would the results be more suitable for application of the cellulose insulated panel. Unfortunately, at EMC 70, many criteria are still failed. However, at EMC 60, shown here, the low reservoir brick now demonstrates improved performance with only potential issues in the mold criteria. Now, when conducting mold checks, you have to define how sensitive the the material under study actually is in WFI. Is it sensitive, very sensitive, not at all sensitive, etc.? In my literature review, I noticed that there is some potential for cellulose insulation to impart mold-resistant properties to adjacent construction materials, such as the wood sheathing or studs, due to the chemicals that are imbued in the cellulose insulation. Therefore, if I were to change the input for mold growth potential on these wood surfaces from very sensitive to just sensitive, the results for mold growth would change significantly, from failing the performance criterion, as seen in the upper half of the chart, to having potential issues or no issues at all, as shown in the lower half. So, let's go back and take a look at our research question. How do masonry moisture storage, initial moisture conditions, and panel type affect the performance of panelized retrofits for solid masonry buildings? As a summary of the hygrothermal performance sensitivity analysis that was created, let's take a look at some of the outcomes we've observed. The simulations conducted demonstrate that the type of brick affects the amount of moisture in the system and how quickly the performance criteria fail. Higher reservoir brick can hold higher amounts of moisture pre-retrofit, which can either be trapped and/or cause potential issues post-retrofit. Lower reservoir brick doesn't hold as much moisture, so we observe less issues overall. While the EMC 80 starting condition is the industry norm for hygrothermal modeling, even this initial condition demonstrates potential issues within the panel overclad strategy with cellulose. In all cases, the cellulose panel simulations demonstrated higher than 20% water content in wood-based products, regardless of the EMC condition. On the other hand, if these wood-based products were substituted and the cellulose was shown to impart anti-mold growth properties to adjacent materials, like I showed in the last chart, the cellulose panel could be a viable solution at lower EMC conditions. Meanwhile, in general, at lower EMC conditions, the SIP panel demonstrates less issues compared to the cellulose-based panel. For research, this work emphasized the importance of proper study of solid masonry overclads with prefabricated panels. While significant energy savings can be achieved through the Energiesprong retrofit strategy, it's crucial that proper consideration be given to the post-retrofit hygrothermal potential of the assemblies. Brick type, initial moisture content, and panel type have been shown to significantly impact the outcomes of the 3 performance criteria studied and should be carefully examined for the exterior panelized retrofit of all solid masonry buildings. For Toronto Community Housing, this research served as a preliminary study of the retrofit potential of a solid masonry townhome, one of many of this archetype. With the abundance of this building type throughout their portfolio, the results presented in this research could help inform TCH about the feasibility of applying the Energiesprong retrofit strategy more broadly. This could serve as a catalyst for the deep retrofit movement that must occur throughout the City of Toronto and beyond. Once again, just want to take a moment to thank the Passive Buildings Canada team for allowing me to present tonight and being so patient for me getting my slides to them. So thank you all.